we'll be ready to go.
Okay, thank you very much. Let me start sharing my screen.
Okay. And just to remind everyone, if you want to ask questions, he needs to be made a host again, Riley. And if you have questions in the audience, just put them through the chat, and make sure they go to everyone, and then we'll address those sort of at the end after Joel's gone through his presentation. Okay. And Joel, are you able to share your screen?
Okay, yes, I'll give me a minute. I think, yes. Can you see my screen now?
We can, yes.
Okay, good. So can I start? We're ready to go?
Yep, ready to go.
Okay, so thank you very much to the organizers. Okay, so let's start with training, beginner training. That probably seems a little bit contradictory, because we'll be finite volume method that usually is something like bands, but I will try to keep it at a beginner level. Okay, so it will be very visual. Okay, so I will not go into details into the concept, but I hope you had time to download the slides, and then later you can follow that. So that being said,
can you make the slides full screen, please?
Okay, yeah, okay.
Here for everyone. Hey, thank you.
Okay, so the first thing is that we're going to go through these topics. Okay, probably I will go a little bit fast because I would like to focus more into the tutorials. But one thing that I want to let you know that let's focus our eyes to train our brain. Okay, so that's why I say I will not go into details into the theory. I will give you some tips and a final recipe. For the SB skin dictionary, probably that is the most difficult one. So we are going to address these basic tutorials. Like, look at that, we have the driven cavity. I think we all know this tutorial, but just by changing the mesh, it's difficult to get convergence. So how to solve these problems. Then also some other cases with strong discontinuities. Okay, source stairs, how to play with the on the relaxation factors. That also, in my experience, I have seen people doesn't understand very well this on the relaxation factors. Then a little bit how to improve gradients in our computation, okay? And then we go to the answer one big question. Should we under relax on the steady solvers? Okay, so we're going to work into this, and probably the final one is the most severe one, that it's a shock wave. So how to put all that numerics. I think the previous talk presentation was something Neil mentioned something about that this is difficult to get it working, but here we have three solvers: steady, zero transient, and unsteady. So we're going to see how to make it work. So now let me go to the actual presentation. Okay, so do you see my screen now?
Yes, we do. Yep.
Okay, so let me move here. So important concepts to remember now before we go into the theory. I hope I think you have done at least once in your life interpolation. So the finite volume method is based in interpolated all quantities. So remember this concept of interpolation. Okay, it's a weighted interpolation, normal interpolation, there is no problem. Then remember this concept as well, the divergence theorem. So is you follow one course in vector multidimensional calculus, probably you saw this this theorem. So this is the basis of the finite volume method. Then remember the Taylor expansion series. Okay, very important concept as well in every single numerical method. And then also all the presentation will be, I will give it using this equation, the general transport equation. But remember that from this equation, we can derive Navier-Stokes equation. So here you see that by simple changing this coefficient, for instance, in this case, you derive continuity, then you can derive momentum equation by changing coefficients. So in theory, the treatment that we're going to see for the temporal derivative, convective stir, diffusion stir, source stir, will be exactly the same disregarding of the equation that you are using, okay? You can also derive energy equation. And then this is what probably will be my main conclusion of a recipe that contrary to commercial software, the CFD software, in OpenFOAM there are no default values. So it is to the user to find those values. But however, by following good standard practices and knowing a little bit the theory, it is a very good starting point. So my final goal will be to give you these default values, this recipe that you will use most of the time and it will work, but then it will be up to you to investigate a little bit more. So let's go now into the finite volume method and overview. So this is general. So for every solver, CFD solver that use the finite volume method, this is the same theory, okay? So it will be Fluent, OpenFOAM, SU2, whatever that use these formulations, the finite volume method. So as I mentioned, we start from this equation, okay? So it's a nonlinear second order equation. So for good accuracy, we want to approximate everything using, in particular, the spatial derivative using second order accurate methods, okay? So we are going to introduce some profiles assumptions that we're going to see that all dependence variables, we're going to assume that they vary linearly about a point P, okay? The point P where we're going to find the solution will be the cell center or the node center, depends on your formulation. So you see that this formulation are about the space and time, it is second order accurate. So this is the starting point. So I will introduce a little bit, talk about fast about mesh data, geometric information, variable arrangement, okay? So we know that we have a mesh, okay? So in structured finite volume method, as it is implemented in OpenFOAM, you can use arbitrary shapes, okay? Any shapes. It can be tetrahedron, X's, prism, pyramids, whatever you want, okay? So the only requirement that you have is that first important, you cannot have negative volume or volume equal to 0. Okay, we're going to see later why, but it's very intuitive. But also the faces that made up these elements needs to be planar. Okay, so those are the only requirements that you have to have in mind. And here you start to see that it's very important to have a good quality measures. Okay, this is the starting point. So we know the solver know everything about this measure. Okay, cell center, face centers, connectivity, areas, volumes, everything is known by the solver. So it's a lot of bookkeeping. There are a few approximations that are introduced as well that we need to know the centroid of this cell, but also the centroid of the faces. So they can be approximated like this, second order approximation. And also we assume that the values of all variables are computed and stored in the centroid of the control volume. Okay, so this is known as the collocated arrangement. There is another variation or that you can find in the nodes, okay? So OpenFOAM is collocated arrangement, and also we assume that all variables are represented by a piecewise constant profile, the mean value, and it's approximated like this. And we see this is also a second order approximation, and see that here you have volume. So this is why it's dangerous to have very small volumes, okay? Because this approximation then will become infinite. So a few things related to the mesh quality. So the input and everything together is a lot of bookkeeping, okay? A lot of information kept by the solver in memory, okay, to do the computation. So now we're going to see how to use this information, okay? So see that we know area, face areas, where this vector connecting two cells intersect this face, so we can know this deviation. We know the normals to the faces, okay? So as I mentioned, there are different formulations for the variable arrangement. So you have the cell centers and no vertex formulations. In OpenFOAM, we have the collocated arrangements, which is the one also used in most commercial software. Okay, so as I mentioned, every approximation that I introduced previously, everything is second order accurate. So before moving now a little bit more into the theory and how to do interpolations, let's talk about the big elephant in the room, which is mesh quality. Okay, we already saw that the volume is very important to have non-zero volumes. So when we assemble the matrices in the finite volume method, we are going to introduce this term, and this term will have an influence in your matrix, okay, in the matrix of coefficients. Later we're going to see that, and see that the larger this dot product becomes, this term will become very large, and that will have influence in your matrices. Okay, so here introducing this in the triangular triangular element, but can be any element. So see that is this vector D and S are aligned. This is an orthogonal mesh. This will become one, so you don't have influence. So the larger this deviation between all these vectors, the more errors that you will introduce in your mesh. So that can be controlled. So now into your numerics, those are some of the tricks that probably I will show you, but be careful that everything depends on your mesh. So this is why it's very important to have good quality meshes. So, and here easily you see that influence. So here we're looking at the actual matrices of coefficients. So this is the output of this problem, how OpenFOAM, the linear solver, will see the problem. So you have this linear solver, and see that as you add some non-orthogonality, see that your matrices become sparse, and it might happen that one of these elements can become very, 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 very large, and it will make your convergence very slow, okay? So this is what the actual linear solver sees. So let's talk about Gauss theorems and phase fluxes computations. So remember this Gauss theorem, very important. So this one, we're going to use it to convert volume integrals into surface integrals, okay? So remember that our formulation of the equation is integral one volume integrals. So now by using this one will be just reduced as a summation of fluxes along all phases, okay? So this is the importance of this theorem in the finite volume method. So we go from here, okay, from volumes to surface. And now that we have surfaces, we know the geometrical information, you know areas, everything, and you can start to compute the famous fluxes, convective fluxes, diffusive fluxes. But also look at that, we're proceeding in a way that first we do everything in space, and then we do it in time, okay? So there is no problem, we can have different order of accuracies in each of the method uses for space and time. So how do we interpolate those convective, diffusive gradients and source terms? So look at that, we have the integral, the formulation, we introduce the Gauss theorem, and now becomes a surface integral, okay? So and this surface integral will become in a discrete language, okay, will become a summation of the fluxes along all the phases. So if you have 4 phases, you will do this loop for 4 phases, and you compute your flux. But see that we still have another integral here. Okay, so this integral can be further approximated using, in this case, and is using in fluent and most of CFD solvers, using the midpoint rule. Okay, so these are Gauss quadrature techniques, so you can use many methods. Okay, and this one is the simplest one, is second order accurate. So basically, you approximate the mean value in the phase is equal to the value now in the phase center. Okay, so this is why we need to know the phase center. Okay, so the whole value here, you approximate it in the phase center. And at the end, you get this discrete expression. Okay, so see that it's just a simple of summation of fluxes across all phases of this quantity, the transported quantity. It can be whatever. It can be temperature, it can be velocity, pressure, whatever you put there. And this is done at the phase. So see that, remember, we're computing a solution at the volume center. Now we need to interpolate this somehow to the phase, that we're going to see how to do that later. We do the same with the diffusive star, okay, same procedure, and we get this. And see that when we do this discretization of the diffusive star, we get secondary gradients. You see that you have a gradient here. So here you need to compute a gradient. So see that this diffusive flux is equal to the summation of this flux where you have a gradient. So this is the importance why we need to compute well these gradients. And these gradients depends on mesh quality at the same time. Gradient, there are many methods to approximate the gradients. Okay, so here we are showing you the Gauss theorem. So see that depends on the volume. So if you have volume 0 here, it will give you problems, those gradients. So there are many methods. Probably this is one to implement, but then in OpenFOAM you also have the least square that in theory is more accurate and actually is more accurate, but sometimes it can be a little bit harder to make converge. But I'm just showing you here the easiest one. And then the sorter is just something that you will add to your right-hand side of your equations. Okay, so you have a sorter, so you can have a linear contribution and also a nonlinear contribution. Okay, so this is something that you add there. So sorter can be, for instance, boundary conditions are actually sorters, or energy sorter, whatever you would like to add there. So at the end, you will have these equations, and then these you can just convert it into your program, whatever you are doing, and you just do summations along all your data, mesh data structure. So now the big question is that we have this, and see that we have all the fluxes at the phases, but we compute it at the cell center. So we know it at the cell center from the initial conditions or the previous iteration, whatever. So how do we interpolate these values the cell center to the phase center. So now we go to the interpolation of the convective schemes. So the first one is linear interpolation. This is weighted interpolation, okay? So weighted means is that you can have a non-uniform measure. So this distance, PF and FN can be different, and you just add a weight there. If it is equal, it's just a standard central differentiation, okay? There's no problem there. So we get this, and you can interpolate the value at F from the nodes P and N. This is the node where you want the solution. This is your neighbor node, okay? So this is very, very accurate. The problem with this is that it might become unbounded for large, let's say, Peclet numbers when the convection is dominant. That most of the cases is dominant. So it will become unbounded. It will add oscillations, and maybe it will diverge. So a solution for that is when we talk about upwinding. Upwinding also is, let's say, a miraculous solution to all the problems. So it works in this way that it knows the flow direction. So if the flow is coming in this way, the value in F, the cell center, the phase center, it will be equal to the value at the cell center, okay? You interpolate it like this, or if the flow is coming in this direction, you interpolate like this, okay? Very simple. The problem with this is that it is first order accurate. It's highly diffuse. It will underpredict or overpredict your results, okay? So these kind of methods, it will always give you a solution, but have in mind for production runs, for your final solution, you cannot use this method, okay? You should go a second order accuracy, okay? So this will give you a very pretty picture, but your results are not very accurate. So there is a compromise between linear and upwind, something called linear upwind. So we can have something like this. So see that, imagine that here you have a cell, another cell here, and another cell here, PP, okay, the upwind cells. So again, it works very similar to the upwind, but now we add a second cell, okay? So knows the flow direction. So is the flow coming in this way, interpolate like this, and it's coming in this way, interpolate like this. So now this is second order accurate, okay? And in the case of strong gradients, it will become upwind. So those upwind solutions, first order, will be computed just locally. So this is the beauty of these methods. It will default to upwind just locally. Okay, so this is known as the second order upwind, linear upwind. In OpenFOAM, it's the linear upwind, sometimes also known as the beam warming scheme. Something that you will see here probably is that here we have a orthogonal mesh, or the cells is the cell centers are aligned, and this is not the case in most meshes. Okay, so this is for orthogonal meshes that is very straightforward to implement. So when we have structured meshes, we need to do some modifications that later I'm going to show you. But this is the simplest implementation of the second order upwind, okay, which is second order accurate. Okay, so this is the method that you should use, at least this one. Okay, you can go higher order accuracy. So these are second order accurate, but however, still they might become oscillatory when you have strong gradients. Okay, maybe you have shock wave or discontinuities, it might become oscillatory. So there is a solution to that. The solution is to add what is known as a limiter function. Okay, that is often refers as a flux limiter or gradient limiter, slope limiter. Okay, they're equivalent terms. Okay, there's a small difference, but it's pretty much, they do the same. What they do is see that this formulation here is pretty much exactly the same as the upwind, linear upwind, second order linear upwind, but we put here a function, and this function, it will compute gradients. Okay, it will monitor gradients, and when detect gradients, it will do the switching to avoid that the solution will become unbounded. Okay, so this is, let's say, the first step to go to what is known as TVD schemes, okay, that are very useful in CFD. Okay, and thanks to that is that we can get solutions in very difficult problems in CFD. So simple take that second order upwind, put a limiter here, and then you need to design a limiter function. So you see here that this limiter function is 0, you will go to upwind. If that limiter function is 1, you will go to the linear upwind. If the limiter function is equal to this function, you will go to the central difference, okay, linear interpolation. Okay, so the idea, those are linear functions, so we can do something like that. I'm not going into details, but I just want to draw your attention to the Sweeby diagram. Okay, Sweeby diagram, you have here the reference. So basically what we do here is that you see the blue region, The blue region here is the high resolution area. So let's say that we want to design a limiter function, this one that we put here, that is always contained in this blue region. Okay, so here you see that you have those famous min-mod, Van Leer, Super B, Osprey. Okay, there are many of these methods. So here I'm just showing you 3 methods. Okay, probably the ones I like. So probably for me, the best one is the Van Leer. You see that it's very continuous. Okay, see, it's a smooth one. Instead, the other ones, the min-mod is known as a diffusive, because see here that is in this limit. Super B known as compressive. It's also in the limit of stability. But these are TVD methods, high accuracy. This is what we want. And see that when I talk about linear limiters, see that the upwind, you make the limiter equal to 0, is a linear one. Second order upwind, so it's very bounded in this region, but then in this small region, when you have a strong gradients, becomes unbounded. So you solve that problem by adding a limiter here. And then you have the central difference also, that in all these regions is unbounded. So this is the idea behind TVD. Okay, so there are many TVD methods with many different properties. I'm not going into details. You have a few references there. So my advice is just you can do your experiments and find your best limiter. But my recommendation is stick with these 4 limiters, which all of them are implemented in OpenFOAM. And my preference is min-mod, Van Leer, or the Venkata Krishnan limiter, okay? So just to show you what is the deal with this limiter, let me show you a small example. So see that we have this example here that we have a passive scatter here that is being convected. Okay, there is no diffusion. So diffusion. So if I sample my solution here, my analytical solution should be 0 here, 1 here, 0 here. Very simple problem, but from the numerical point of view, very difficult to solve. So here's where we can see how these TVD schemes work, okay, in action. So if we compare all the TVD schemes, okay, the non-linear ones, Super B, min-mod, Van Leer, the ones I like, see that all manage to resolve very well that discontinuity, okay? Even as you see that you have here some diffusion, okay, so this is numerical diffusion. It's a very good approximation for this such severe problem. And then we can compare with the linear one. So see that upwind is very diffuses, and this is numerical diffusion, okay? So you are diffusing your solution. Then the linear wind, that it is very good, okay? It is a very good agreement, but we know that it might happen that it might oscillate when you have a strong gradients. So if we put everything together in one single plot, see here that what we have. Okay, so see the linear wind is very diffuse. If it's almost 20%, you are just under predicting your solution. In this case, that is too much. And then you have all the others, including the linear wind. You have it here, and see that you have the linear also, that is oscillatory. It's very accurate. You can compare the accuracy with the Super B, but the problem is that it is oscillatory. You see the oscillations there. So it might happen in my case. Usually most of the time I work with aerodynamics, okay? So sometimes I don't care about this. But in your case, if you are working, for instance, chemical reaction or combustion, this is unacceptable because you might be triggering an artificial reaction just because you have this numerical oscillation. So be careful. And here is where you should put those TBD, okay? So it's always, it is not necessary to use TBD always, okay? It depends on your physics, okay? But if this is your case, it's better to go TBD. So that was just that introduction to that interpolation. So now let's talk about the same interpolation, but in a structured measure. So I talk about that these cell centers that work collinear, but most of the time it might happen that they are not collinear, something like that. Okay, it still is the same orthogonal mesh, but see that the minute that this cell center is not aligned anymore, we need to think about another formulation of how to do that interpolation. The principle is the same, but we add new different terms. Okay, we want to erase this term. We don't want this term anymore in the equation. That is one of the approach. Okay, by the way, this is an area of active research. There are many techniques. So for instance, you have these techniques here that you can express the upwind, central difference, second order upwind, and quick, another method, high order, like this. So see that here, not anymore, we have the cell PP. Now we have gradients. So you are introducing the cell gradients. That is actually what happens. And probably you are familiar with this formulation we saw at the beginning, okay? And maybe you will see that as you add a limiter here, you will make this more stable, okay? Or maybe you have heard about the bars just percent, something similar. So see that now by adding the gradient of the cell, now we don't depend anymore about the PP. So this is for constructor meshes. Now also the rate of successive gradients can be computed in this way. By the way, there are many ways to do it. I just proposing this one, okay? You have the reference here. So you can compute it in this way, and then you can monitor the gradients. When those gradients, this ratio becomes 0, it will default to upwind, it will give you a solution. When it's not 0 or larger than 0, let's say, because also when it becomes negative, it will be upwind. More than 0, it will be second order accurate. And remember, this is something local that you do. Another way, popular way, I mentioned the Bas-Jefferson. So Jefferson, something like this, like the linear, you add the limiter, and then you reconstruct from here, from the cell center to the face. Okay, see that you are introducing the gradient. So here, the gradient of the cell to reconstruct the value at the face. Okay, and there are many here. We have seen that you can add many limiter functions. So the popular ones are just Mimma, Bas-Jefferson, and the Venkatara-Krishnan. So just to mention that the limiter function, the slope limiter, gradient limiter, can be related to the flock limiter. There is a slight difference I mentioned in this way. I'm not going into details. So here you have some references. So now let me go about interpolation of diffusive fluxes. Okay, so probably these are the easiest one, the easy one, because it's the Laplace equation, which is a smooth equation, but it gives problem for the gradients. So what we need to do here, so in this case, this is an orthogonal mesh. You have an orthogonal mesh and uniform, okay, that this distance is equal to this one, you can approximate like this one, okay? It's very easy. But when the mesh is non-uniform or when you have non-orthogonality, you need to add corrections. And those are those famous corrections in SV skin that sometimes are confusing. So the non-orthogonality is this angle, the angle between this vector S and this vector connecting the cell center. So you see that if this angle becomes 90 degrees, the cell volume is 0. And that's why we have always run check mesh and check your mesh quality, okay? If you are close to 85, probably it's a good idea to reduce the mesh, because we know that this will have an influence in the gradients, and the gradients, we have it all around in the approximation of convective and diffusive term. So just to show you a way how to correct that one, this is the over-relaxed approach, which is actually the one used in OpenFOAM. So you can compute in this. So look at that, everything is geometrical, okay? So by the way, this angle is 40, okay? You see the angle between this vector and S is 40 degrees. So you can correct this, and you can divide this gradient in an orthogonal contribution and non-orthogonal contribution. Implicit part, explicit part, okay? So this will be in your left-hand side, right-hand side when you assemble matrices, okay? So this is the problematic one, that is, if it becomes too large, you see here as K keep increasing, this one might make your solution diverge. Okay, so something important to mention as well, when you have orthogonality, always you will have a secondary gradients, okay? And this secondary gradient is the one that we need to correct, the problematic one. So whatever you see a Laplacian in your equation, you will have this secondary gradient. So probably the most famous one is the one with pressure, okay, that we are used. But if you are working with compressible flows, also in energy equation, you have this Laplacian, this secondary gradient that is critical. And if you are using Torrance models that probably you are using also all around your governing equations of Torrance models, you have this Laplacian, and you will have this secondary gradient that you have to be careful. You need to correct it to avoid numerical problems. So now let's talk about gradient computation at cell centers and gradient reconstruction of phase centers. So we mentioned that we can compute it like this. There are many ways, as I mentioned. This is probably the easiest one, but it's second order accurate, okay? So it's just a summation of the fluxes along all phases, okay? You can reconstruct it. And again, remember that you need good quality meshes, otherwise you might have problems with this gradient. Then somehow, this is the gradient in the cell center. Probably somehow also we need to reconstruct it at the face. Again, there are many methods. We saw this many reconstruction methods. So you can go linear and in a uniform mesh, okay, where P and PF and F and NF are the same. You can use this one, okay? Very accurate, okay? But this is a section rather than the rule, okay? Most of the meshes are non-uniform and you have no orthogonality. So you need to use another method. So non-uniform meshes, you will go like this. So this is something that is you recall of the scheme. This will be orthogonal correction. This will be the limited one correction, okay? And then if you have non-orthogonality, you need to correct for that secondary gradient, okay? So we saw that one method, but also you can do a reconstruction like this. This is very, very clever. I really like this method. So see that you have the values in P and N. What you can do is reconstruct it in some other fictitious point, but you are making sure that when you do this fictitious point, when you reconstruct those values here, this vector connected P asterisk and N asterisk will be normal to the face and will pass through the face center, okay? So it's a very clever reconstruction. So as you see, there are many methods available. And now just to also to give you an image of what are those gradients, slope limiters, gradient limiters. So when you are reconstructing the gradients at the faces, it might happen that the gradient will be larger than the two values that are bounded this one. So see that you have the gradient in P and N, and your value should be bounded between these two. Cannot be larger or smaller, but it might happen. And this can happen due to skewness or non-orthogonality. So what our gradient limiter is doing here actually is just, if it detects that this value is larger than the bounded quantities, it will clip it. That's all, okay? So if it is unbounded by the values 1, clip it by 1 and put it here. And also if it's here in the negative. So that is, okay, very brutal, but it works. And here also there are many ways. Probably you have seen the ND keyword, like multidimensional or directional, okay, cell limited, phase limited. Those are different ways to do this limiting here. So there are some that are very aggressive. There are some others that are less diffusive. I will explain that later. So now we go. Okay, so this is just to show you the effect of the gradient limiter. So probably later you can see this one, you have the reference there, but you see different gradient limiters can give you different outcomes, and probably some of you in steady simulations suffers a lot that the residuals are stalled. And this is a very well documented behavior that it can be solved by using a different gradient limiter, but this is not a problem, okay? This is just studying that, okay, you have something on steady there. So, okay, so just to summarize, mesh-induced errors, you can have non-orthogonal mesh and skew mesh, that is this. So non-orthogonality, we have seen that is this angle. Skewness is this deviation, probably just to make it clear. So you have the vector P and N, okay? So you have it like this, and then this vector will intersect the face here. But actually you want to approximate the solution at the face center. So this deviation here is what we know as skewness, okay? And these two errors, non-orthogonality and skewness, will have an strong influence in all our approximations as we have seen. So this is what we want, okay, as I said, but this is the section. So usually you will get meshes like this with this error. But as you do, that is the best advice that I can give you. Try to get good quality meshes. So now that we did everything in the space, we can move to time discretization, okay? So this is when you proceed, this is something like method of line, okay? So you can use different order of the discretization methods, okay? So you go in space, and then here in time, you can use any methods. There are many methods implemented. So just to mention Crank-Nicholson, Euler implicit, forward Euler, backward difference, and Adam-Basford, Adams-Moulton. So there are many methods. It's up to you to choose one, okay? One thing here that also diffusion applies in time. So talking about first order approximation, second order approximation is important. However, it's less severe. So actually in time, you can go get your way around using first order discretization with no problem, but have in mind that you need to keep your CFL less than 2, ideally less than 1. But you can do it and you can get same accuracy, okay? So the last part is that we assemble everything. When we assemble everything, we are assembling those matrices. So now we crunch numbers. So this is the linear system solution. I'm not going into details here. tomorrow, I think there's a very nice presentation, so follow that one. So basically, when we assemble that and we are getting coefficients and phase areas and volumes and intersections and everything, you are just getting these coefficients. So the diagonal, okay, is your solution. You want to compute the solution, node 1, 2, 3, whatever. And the off diagonal are all your contributions that are related to your mesh quality. So remember at the beginning, the dot product S divided dot product SD. This is that the influence. Plus also you have the influence of your transported quantities and properties of the fluid. So this is your matrix of coefficient. This is your your solution, and these are the sources. Can be boundary conditions or something additional. So this is what we assemble. So we have left-hand side, right-hand side, okay? And what I mentioned that this is important. You need to have good quality measures because the matrix A depends on this, okay? So the larger this deviation are here, you will start to have strange stuff that will make your linear solvers to converge slower, or even make your solution diverge. So these are the actual matrices that you get. So this is a matrix for orthogonal mesh, and for unstructured mesh. This is the actual matrix now for a case in OpenFOAM, okay? So you can dump those matrices, okay, and you can analyze. And so it's an importance when in linear solver that is ideal to have matrices, okay? So when you have a banded matrix like this, your solver will iterate faster. So this is the famous renumber mesh. This is what you are doing, okay? But again, you can have strong banded matrices if you have good quality meshes. And something important when this matrix is that we want, as you see here, we want to be diagonally dominant. And this is a very important property in CFD. Okay, so a diagonally dominant matrix is this. When you satisfy this requirement, you can say that is diagonal dominant. And when you have a diagonal dominant matrix, we are sure that we can get a solution, okay? And later that can be related to something called the Scarborough criterion, okay? So I will give you a reference, but if you your matrix is diagonally dominant, you satisfy this Scarborough criterion, you know that your iterative solver will converge. But this diagonality of the matrix is related to the mesh quality and also can be controlled by using under relaxation or reducing the time step. And this is why you see when you have a smaller time step, you have a better convergence because you're making your matrix diagonally dominant. Okay, and also you can play around and you can add sorter to modify the dominance of the diagonal. Okay, so here you have a few guidelines, the reference. What is important about this Scarborough criterion is also used to implement boundary conditions and sorters, okay? We'll give you some discretization rules that you have here. So then you assemble everything for every single, this equation for every single node, okay? You assemble everything, so now you can iterate. So you start from an initial condition, okay? Your folder 0, you iterate, reach your tolerance, your final tolerance, and then you move to the next iteration. Can be iterative, steady solvers, or can be tiny step on steady solvers. And this is how you proceed. So what you get here, these are your initial residuals, okay? So your initial residuals is always the previous iteration. And when you see that the initial residuals tends to go to the final, you can say that you have a steady solution, but that is the exception rather than the rule that we see better here. So you start to iterate. For instance, here, this will be your initial residuals, boom, 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 and you keep going like this. So always your linear solvers will reach the convergence criterion, okay? When they reach this convergence criterion, they move to the next iteration. Use previous solution as a starting point and keep iterating. Usually, also don't be afraid. Some people is afraid sometimes that see that the initial iteration, they do not converge. That is normal, okay? Probably the first 10 or 20 iteration might not converge well, okay, but then they speed up, okay? That is a normal behavior. Don't be afraid of that. Be afraid that your final iterations are final residuals, okay? I'm not talking about initial residuals. Final residuals, if they are not converged, that is dangerous, okay? Because you are losing accuracy, but just into your final iterations. Okay, so let me skip here. Later you can follow this one. But this is actual matrix, how you see the matrices and your coefficients. And just to talk a little bit about the multi-grid and Newton-Kirchhoff solvers, okay? But again, tomorrow there is a talk about this. So usually multi-grid is a way to accelerate how the linear solvers are, the convergence speed. But honestly, in OpenFOAM, I have found that not always is the best option. And sometimes if you are dealing with multi-phase flows or highly compressible flow, high speed compressible flows, probably it's better to use Newton-Kirchhoff methods. So these are things that you may discover with just playing a little bit with different model cases. But here, just to mention that in theory, the multi-grid should be the fastest one, but sometimes, depending on the physics, sometimes the convergence can be slower, okay? You will arrive to the same solution, is the convergence speed. Okay, so just to end up here, so what does a finite volume solver do? So basically we'll just get mesh information, boundary initial conditions, physical properties, all these physical properties, and most of them you will interpolate it from cell center to phase centers, physical models, okay, so you assemble equations, then you need to say how to discretize in space and time, okay, then how to solve linear solvers, and then set some runtime parameters, okay. Every single solver will do that, however, in a different way, using a GUI or a text interface like you know. Okay, so that is the general overview. Remember, it applies with every single solver that use collocated arrangement finite volume method. So now let me go into the specific part of OpenFOAM. And basically here, OpenFOAM will do those steps that previously mentioned, but remember that your mesh is located in polymesh. In constant, you will have physical properties. In system, you will say how to do discretize all the terms, okay? In zero, you will have boundary initial conditions, and in control D, you will have all these runtime parameters. Time step, okay, to control, to make, let's say, your matrix diagonal dominant, and the under relaxation factors you have in FV solution. So we're going to play with that in the tutorials. Okay, so if you go to SB scheme solution, just to explain to you, so as you see DDT schemes, this is what you are actually solving, and you have many methods. When you have gradient, this is what you are solving. When you have divergence, this is what you are solving. We saw the theory, we know what to choose. Laplacian, these two SN gradients and Laplacians are related, and interpolation schemes, how to interpolate from cell centers to phase centers, usually related to the physical properties. So now this is what we need to choose, and I hope you got a visual idea of how to choose those parameters. So just to explain, in OpenFOAM, you have many methods, okay? Honestly, most of the time, you will stay in these four methods, okay? So steady state, you want a steady solution. Then Euler backward Krenz-Nichols. So most of the time, honestly, I use Euler, and I keep my CFL number less than 2. Then when it goes to convective terms, there are more than 50 terms, okay? So don't get lost there. Here, basically, you will need upwind. We know that upwind will always give you a solution. So you can use it to get initial solutions or to stabilize your solution. Linear upwind, second order accurate bounded. Honestly, most of the time, this is what you will use, okay? Very accurate, very good. And there is a variation called V, which is specially formulated for vectors, okay? So it is more accurate, but tends to be a little bit more oscillatory, okay? But this is one you can play around with this just for vectors field. But you can use this one in vectors. Then you have linear. We have seen that it's very accurate, but it might be oscillatory. Then you have an option. You can get a bounded linear, okay? So just to reduce these oscillations, you can use something that is known as limited linear, especially recommended for less simulations, okay? So this will be kind of similar to the from method, as you know, the theory. And then choose a good TBD method. My advice is stay with these two, Van Leer or min mod, okay? And that's all that you need to know, okay? Depending on your physics, you can just change this discretization. And lately, I have been playing a little bit with this method, the LUST, okay? It seems to work very well, but honestly, stay with this one. Just to make clarification also that the gradients, when you use the linear wind, you need to add this keyword. Okay, we have seen that in the linear wind, you need to give the gradient information. The R is this one. So you put here and you say how you want to compute it, okay? So that is just to make it clear. So then you go each grading, how to discretize the cell centers. So every method that you will have in OpenFOAM, probably I'm missing a few ones here. Okay, I didn't update it, are second order accurate. Again, you need to use all of them. Most of the time, I just stay with Gauss and least square. And then you will have the grading limiters, and you will have these keywords. Okay, so cell limited, cell ND limited. So ND is the multi-directional, means that it is selective. It's less aggressive than this one. Okay, so this one's very aggressive, less aggressive. Okay, and then there are some other methods, like you have the qubit and Venkatakrishnan, also you have it. So here you have how to use it. So probably you will use this, the qubit and the Venkatakrishnan, you will use it when you have very severe problems, okay? But most of the time, incompressible flows, do not go for those methods. So as I mentioned, stay with Gauss and least square and cell limited. Most of the time that is okay. A small warning that be careful not to add very aggressive limiters to pressure, because if you are pressure, temperature, energy, because if you are interested in computing accurate force computation or heat transfer rate, you put a very aggressive limiter. Let's say this one have a blending factor of 1. It might add a little bit diffusion. Okay, be careful about that. So that blending factor, actually, okay, later I will mention that, is this. Okay, so when you do this, the formulation, default, this is your gradient limiter, and then here you put a blending factors. You put it 1, means that is always on. If you put it 0, it's off. Okay, so 1 is very aggressive, and sometimes if you put it in pressure, you have it default, it will also do it for pressure. It might add some diffusion for your forces. So be careful about that. Then we go about diffusion terms. Okay, so we have here many methods. So usually orthogonal, never uses just perfect meshes. Okay, so go for corrected or limited one, as we're going to see. So if you are using corrected, this is what you are solving. But as you know that if you have no orthogonality, this will add a lot of error. So you stay with this method. Okay, so you have the limited. Okay, so usually orthogonal, you put it in these meshes, then limited one or corrected is just for the non-uniform meshes, but also non-orthogonality. And then you go like this for instructor meshes, it's just recommended limited 0.5. Okay, so you have there your recipe. Okay, so here you play around, but here go limited 0.5. And what is important that this 0.5 is just to guarantee that the non-orthogonal contribution will never exceed the orthogonal contribution. And why that is important? Because this is explicit. And if this one becomes larger than this one goes to your right-hand side, and you will start to have problems with your matrices. It will become, no, you are not going to satisfy this Scattergood's criterion and that stuff. So you put that 0.5 is just to limit this. Just it will not be larger than this one. That is what you are doing. Both these two coefficients, they are just computed in the same way that I showed previously, but then you just limit it by that value to avoid that quantity to become larger. Okay, so these are the methods. So later you can read it at your own pace. So what method should I use? So this is my advice. You put here Craig-Nicholson 0, okay? So you have a coefficient Craig-Nicholson. When you put it in 0, means Euler. And then probably at a later time, you can increase it probably to 0.7 to get extra accuracy. Then see that you have gradient limiter. So here I just put in a very aggressive limiter just in velocity. Usually that is what you need to do. And the rest of the variables 0.5, not so aggressive. But if you want, you can go aggressive in all of them, but have in mind that you might start to add a little bit diffusion. Then see that phi of u, the convective, you use linear upwind. Okay, here I'm using B formulation for vectors, but if you want, you can use the normal one. Okay, the V is just specifically for vectors. And the rest of the variable, the turbulent variables, okay, linear wind, but you can use a wind with no problem. Remember that turbulence is a diffusive process, so if you use a wind, it's not having a heavy impact in your solution, okay? There is no problem. And then limited one means that it's a good quality mesh, but it's your mesh start to go when you run check mesh orthogonality, let's say more than 80, or more than 75, put here 0.5. Okay, then if you want something very accurate, you can go like this, but have in mind that this is might be very oscillatory. So usually this is something that you will use with less simulations, okay? And probably instead of linear here, you will put limited linear, okay? Probably unless you don't have omega and k. Maybe you might have k, but omega you don't have it unless. So this is something very accurate, but have in mind that it's very oscillatory. And something that it will give you always a solution is this. Okay, so see that this is first order accurate. So if you are running your case and you see that it's exploding, diverging, you just go use this method. And if the solution is still diverging, the problem is somewhere else, because this should always give you a solution, okay? So you should check physical properties, boundary conditions, the compatibility of the solver with the physics, but this should always give you a solution, but it's highly diffuse. You will underpredict or overpredict your solution by a lot. So that is the recipe, okay? So just to end it, and just to give you some kind of conclusion, okay? So good mesh, good results. That is the most important thing, get good meshes. Start robustly and end with accuracy, meaning that you can start your solution at win, and then after a while change to linear win or limited linear or whatever you want to use, but second order accurate or higher. Okay, perfectly valid. Stability, accuracy, and bounding. We study with all those concepts. So if you play by this term, ensure that you will succeed. You have that recipe, and ensure that that recipe will give you always a good solution. And something very important, do not sacrifice accuracy and stability over computing speed. This is very important because everybody wants a solution for yesterday, but it's not possible, or it is possible, but you will lose a lot of information, okay? You will add too much diffusion. This is particularly for the linear solver, so SV solution. Okay, so just to go fast here in this one, then I will have half an hour for the tutorials. What else we did not cover? A lot we did not cover. So you see that these are a few of the selections that we didn't cover, but the recipe I gave you, I think will give you, it will make your cases work. Of all these topics, let me briefly address this one, pressure velocity coupling, just to show you a few things here. So this is how we couple the equations, the governing equations, okay? So you have seen simple C, piso, and pimple. That is something particular for OpenFOAM. I prefer to call it iterative piso. Okay, so this is how we couple the Navier-Stokes equations and how to solve those. But there we have a few loops. And look at that, when we manipulate the equation, see that we have the Laplacian of pressure, and this is the one that we have this secondary gradient that we need to be careful with that. Okay, so whatever you have a Laplacian, be careful because it's heavily influenced by non-orthogonality mesh quality. But the thing is that you have this loop, and this is a particular in OpenFOAM. See that just to here, when you do solve the pressure equation, just to correct for this secondary gradient, you have the non-orthogonal corrections. And then you have another momentum correction, okay, pressure momentum correction. This one will give you better approximation. So see that here you start to iterate using value 0, but here you get you get a prediction and you give it back here to this one to get better approximation. So always look at this because you can improve your solution a lot. And here also you can influence your convergence speed here. So some people tend to put this on 1-1, which is fast, but it's not a good idea. So sometimes it's 1-2, okay, to get better approximations and to reduce this error, okay? Whatever you have a Laplacian, see here that this is in temperature or can be your tolerance variable, it will add some error in your solution. And these are the specific loops in OpenFOAM, okay? So you see that you can under-relax, okay? And you control here in non-orthogonal correctors. This is just for simple, okay? That in OpenFOAM is formulated for steady solutions, okay? So this is the only variable that you need to put. Non-orthogonal correctors, okay? My advice, always put at least one. Even if your mesh is perfect, at least one. You start to have bad quality meshes, 2 or 3. Don't go more than 3. It's better to reduce the mesh. And then remember that you control the steady solvers using on the relaxation. So closer to 1 is faster, but oscillatory. Closer to 0, very stable, but very slow. So this is very problem dependent. So here I'm giving you the, let's say, industry standard, okay? So most of the time these are okay, but sometimes you will need to just play around with this a little bit. Then you go to the piece of loop, okay, just to mention. Then here you have the same function, but now you have these n correctors. My advice, always put 2 there. So this ends this one to get better approximation of this equation that is very important, okay? And then the piece is pretty much the same. Let me go here. So this is the piso and pimple, okay? Piso non-iterative, that is recommended to use with a CFL less than 2, by the way. And then you have piso iterative, very robust. And see that the difference here, this is the pimple, that you have this simple loop. So this simple loop will add better corrections, okay? So my advice here also is to do at least 2 of these correctors. The other keywords works in the same way, but do at least 2. And then yes, you can under relax those equations, okay? And you can use the same under relaxation as you use for a steady, but do not use too low values because you start to lose time accuracy, okay? You enter into a pseudo transient that is not time accurate anymore. So that was all of the theory. So here I'm giving you some reference, that later you can go into details. And okay, so let me go, So I will do the tutorials. Just follow me, okay? If you download, you can follow me, then you can watch the video. So there are 7 tutorials. I will show you what we're doing. So just to be sure, do you see my screen?
Yes, we do. Yes, we do.
Okay, so we have here 7 tutorials. So let me go different tutorials and try to, so let me go first to the driven cavity, okay? So very easy tutorial. And if I go to orthogonal and just to, in every tutorial, you will see these scripts. So if you type just SL run all, it will run automatically everything. If you are a beginner, my advice is just to open this file and see the steps, okay? So you see the steps, the post-processing, how I'm doing everything. All these tutorials also I'm using a robust numerics. So see that this is the driven cavity. You are familiar with this. We have a reference solution and OpenFOAM solution. Very good agreement. But this is with a good quality mesh. Okay, so let's see the mesh here. So look at that. This is a perfect mesh, a section rather than the rule. So now let's use a non-orthogonal mesh. So this is, you see here the Kirchhoff mesh. So let me go there. And first, let me generate the mesh. Okay. Okay, let me run everything. It will diverge actually. You have the case and it will diverge. You see here the reference solution, but not the actual. It diverges. So these are the problems that many beginners can have, okay? So how do we control this? And just to see the reason, if you open the mesh, okay, now before opening, if I run check mesh, see that check mesh is just telling that this mesh is okay. Look at that non-orthogonality is in the limit of a good quality mesh, it's 70%. This mesh is okay. But when you visualize the mesh, you will realize by no standard, this is a good mesh. So see that here you have all problems all together. You have skewness, non-orthogonality, non-uniform meshes, okay? And this is why we need good quality meshes. Such a simple problem, it is just diverging due to mesh quality. So how we can make this problem converge? So we already know that the problem is non-orthogonality. So let's go and let's take a look at SV skins. So see my SV skins. See that I'm using a method orthogonal in a mesh that is not orthogonal. So this is the first modification. And always my advice, go here, limited. Okay? So limited. So let me rerun. And it diverges again. But it ran a little bit more. But see that a little bit more and see that the quantities are very bounded. Previously, you realize that the probably you look the previous one, the CFL, it was something almost infinite. See that this is bounded, but it's almost there, it's still diverging. So now the problem that we have is you go into SV skins, remember the corrections, we need to increase the correction. Even if we're using 2 non-orthogonal corrections, okay, if you put here 20 or 10, it still will diverge. Now your problem is that we need better approximation here, and that you control that here in correctors. So see that if I put there 2, let's see what happened now. it run. It will be slower than the previous one because it's doing now 2 iterations. See that here you have iteration 1, iteration 2. If you put 3 there, 1, 2, and 3, and those iterations might be expensive, but you are gaining stability. And that is my advice, okay? Do not sacrifice computing time over accuracy and stability, because you might get the wrong solution or it might diverge. So
Nice.
see that by just doing those 2 simple modifications, we got a solution, and see that we have a very good agreement, okay? Remarkably good in a mesh that is not very good, that you have a lot of problems living all together, okay? So this is the first tutorial. So this slightly orthogonal is similar, okay, but it's less severe, but you will see that it will suffer similar problems, okay? So you can play with that as well. And actually, just to show you, this is the mesh that you are going to have. So you have this mesh, okay? So here you have non-orthogonality. It's less severe, but still you have problems with getting good solutions, okay? So this is my recipe for the Laplacian. Always use limited 1 or limited 0.5, okay? So now let me go to the second one. And is this one, Laplace gradients. So remember that we talk about, we want good gradients approximation. So let's see how we can get better gradients according to the mesh type. Okay, so if I go there, Laplace gradients, we are going to have, so you have the automatic script there. So we'll run 3 meshes: quads, triangles, and polyhedral cells. We are going to get exactly the same solution, but when we look at the gradients, what is behind doors, we're going to see that the gradients are approximated in a different way. And in some cases, those gradients will be the responsible of making your solution diverge. And we're going to see here, okay? So let me launch ParaView. Also, when you see here the folder ParaView, it means that here you have an state that you can use to reproduce the same visualization I am using. So if I go here, load state, ParaView, you load this state. You need to, oops, sorry, you need to choose the files now where the case is location. So I will choose this here, C2. And let me go to C3. Okay, so depending on your computer here, you will have different paths. That is what I'm doing, okay, reading my path. So see that it's reproducing, and see that the solution is exactly the same. You have 3 quads and poly. So there are a slight difference, but less than 1%, by the way. So very small differences depending on the mesh type. So we can say that this is good for all the meshes. However, when we look at gradient information, you will see that they are very different, the gradients that we compute. So if you go here, I will plot in particular grad T Y, okay? Then and see the gradient. So see that the triangular mesh is the quad mesh is smooth. Okay, this is smooth, but the other 2 meshes, it is oscillatory, okay? Even if your solutions are perfect, you have this oscillation, and sometimes this oscillation might give you problems. So how do we correct that? So by the way, just to show you the meshes, let me go here. Okay, just go here. Quad mesh, so now we see this one. Triangle, okay, this is a polyhedral mesh, and this should be triangular mesh, I guess, and triangular mesh, okay? So these are the 3 meshes, and in every single one, it's clear that the gradients are computed differently, okay? So how do we improve those gradients that are computed behind doors? So I will work just in C3, which I know is the polyhedral mesh. So you go again into SB schemes and SB solutions, okay? So see that the gradients are using orthogonal method, okay? So again, I'm using a method that is not ideal with these kind of meshes. So my advice on structured meshes, stay here, linear limited 0.5, okay? And this one also here. So you have some comments there as well. And then let me use also something better than linear, least squares. So now I use least squares, and remember that always you should also add a couple of corrections. So one correction is okay here. I'm not going to increase that. Okay, so I will rerun, and we're going to see the effect only on the polyhedral mesh, but the triangular, then you do the same, and you will see that you will smooth those gradients. So particularly, let's say if you are doing compressible flows, it's just very important to get smooth gradients. Okay, so we have the solution. Go here. So load your state. Choose the file names. So I have it here, C1. Go to C2. And now go to C3. Okay, we have the tree, the solution. See that it's exactly the same. But now let's go back doors and let's look at the gradients. So let's see how we have improved those gradients. So that one. Okay, see that? Okay, let me hide one that is, okay, no, this one. Okay, the legends do not correspond to the actual cases. Okay, the quad should be the black one, and the red one should be the polyhedral. I need to update the names, but see that you recall the previous one, it was very oscillatory. See, by just adding the right discretization and improving the gradient, see that we have better gradient computations. As you see the other one, okay, this one. Look at that, the previous one, it was something like this, very oscillatory. Even though if your solution is the right one, you have something in the background that sooner or later might influence your solution. So my advice also, be careful, and be careful with the gradients. Particularly, they are very important. Okay, so I end with that tutorial, and let me move with the 2D elbow passive scatter. Okay, so here I will work it out to just show the influence of under relaxing and on a steady solver. Okay, so I think I'm running out of time, so I will do this one, and then just to show you something about the most severe one, the NACA 0012. So I will go into piezo eta. Okay, so see that if you go here, so you will start to see from now on that I'm using a good numerics. Okay, so this is the Reynolds is low, viscosity low, so Gauss linear, but see linear win the formulation for vectors. Okay, you can use the standard one, and see the limited one. The mesh quality is okay, but the importance here is that you can under relax the solvers here. Okay, so you can say on the relax all quantities like this. So I will choose, so remember that under relaxation, it will make your matrix more diagonal dominant. So this is very important to add. But if you choose a value very low, your convergence will be very small, very slow. And also you will lose time accuracies you are working with on steady solvers. Okay, so let's see the influence of this in the solution. Okay, so if I go and I run here, and see that you are, this is the pimple, okay? See that you are doing outer iteration. See the pimple iteration, 1, 2, 3, 4. So it will do this many iterations or until reach this convergence criteria. And honestly, I recommend you to use this solver if you have complex physics, okay? but it's more time consuming. See that it will take, in this case, it will take 9 times longer to get the outcome if it's still iterating in 9 iterations. But usually when you keep, you see that now it went to 2 iterations, okay? So I always recommend you do at least use the pimple or the iterative piso, and you do at least 2 iterations. So proceed always like this. And under relax, but do not be too aggressive with this under relaxation. So we go here, look at the solution. So by the way, what we're injecting, so the classical now pipe to the pipe, and we're injecting a passive scalar here and here, and see what happens. It is being transported, okay? Well, actually the under relaxation didn't enter into action. So I didn't, I think, okay, I didn't save. So, okay, we have now the solution. Okay, so remember the solution was with under relaxation 0.5. Okay, we have, in theory, we have here time accuracy. This is time accurate. Even if it's 0.5, I recommend you to use 0.7. Okay, so now let me go here, 0.1. Okay, now I save. Let me run. Exactly the same. So in theory, this is more stable. However, you are going to lose time accuracy, and you will need to iterate much, much longer to let that passive scalar come back up to the outlet of your geometry. But yes, it will give you, adding relaxation factor will give you more stability, but be careful that you can use your time accuracy. Okay. One standard practice also, you will see in all my tutorials, I always like to print minimum and maximum values, because this is a good indication on stability. If you are running and at some point you see pressure becomes 1 million, you know that you have a problem. And probably you can have the pressure 1 million and it will keep iterating and it will give you a solution, but it will be the wrong solution. So always add that one and monitor your solution. So we have a solution here. Apply. And S1, and if I press play, see that now it is converging. There is no problem, but see that you lose your temporal accuracy. Okay, and maybe if you let it iterate up to 600, you will see that you will reach the same solution as the previous one, but this one is not anymore time accurate. So this will be a, let's say, a pseudo transient. Okay, but yes, I highly advisable. My advice, put under relaxation and put here 0.7. Okay, you are not losing any time accuracy. Okay, and actually the recipes that I'm giving you are equivalent to the faults that you will find in commercial software. In particular, I'm using the same ones as the one that you will find in Fluent, in ANSYS Fluent. So let's go to the last case, which is interesting one, probably the most severe one. And it's interesting that as you follow the presentation by Niels, he mentioned that it's very tricky to get compressible flow solutions, aerodynamic, aerospace engineering, in particular. However, as you have seen the theory, is you manage to work out how to set your SB scheme, SB solutions, you can get solutions, and I will show you here. So here you see, you will have, using SimpleFOAM, PimpleFOAM LTS, local time stepping, and then you have PimpleFOAM, okay, this is fully unsteady, wall modeling and wall resolving. Both of the cases, it will give you a good solution, okay, accurate solution, okay? And just to show you, I will go with the wall modeling, and let's see the case setup. So if I go raw PimpleFOAM, and probably we're going to have time to post-process. I will run, but in the meantime, so this one is running also, will run in parallel with 4 cores, so be careful. So basically, look at my So first, let's see the mesh. Okay, so what we're solving. Okay, so in the next 8 minutes, let's try to do this. So we have this mesh, okay? Everything done using block mesh. So you see very nice mesh, but here we're going to have a shock wave. So basically we have the flow entering here. I think it's 2 degrees, 1.5, I don't recall, but we have a shock wave, okay? It's Mach number 0.8, or no, I don't recall. So these are tricky. So see that I'm using Euler, and the intent is that some people say that you want fast solution. I see that the case is running CFL 10, and actually as you go in this case, you can go with up to a CFL of 50 and it will run fine because we're using the right numerics, okay? We're going to check that. However, your final solution, you should be careful because you are adding too much numerical diffusion. So see here that you go SB solution, see that we are adding the pimple with the convergence criteria, consistent formulation that is more stable than the simple normal. So this is the simple C. Transonic is another correction for highest peak Mach number, okay, for high Mach numbers. And see that 3 correctors, 20 outer correctors, okay, on the relaxation. SB skin, see that I'm not adding a very aggressive limiter for pressure. I know that I want more accuracy, so, but the rest, see that I'm using my limiter. Then I'm using, in this particular case, the min mod, the normal definition. Also here you have the V, but also you can try it later with linear win V, and you will get a slightly different results, but all of them will converge. And if you want, you can do it with a win, it will converge. And actually with a win, you can go CFL up to 100, but you will add a lot of diffusion. And see that the rest, okay, usually for energy, you can go and use the limited linear, okay? I have found that it's very stable, okay, and very accurate. But you can go linear win, but stay with this one, it's very stable. Limited 0.5, even if the quality of the mesh is very good. Remember, this is my recipe, 0.5 here. See that it's running, no problem, CFL 10. And this is the point that people will say, but it will take me forever. This is the price that you pay, okay? And this is wall modeling. As you go wall resolving, the situation exacerbates. These times that will become an order of magnitude lower, but again, you can increase that. So I can increase that one. Let me go. And this is very important advice. Do not go and put here 20 right away because it's likely, probable that it will diverge. So you need to do these increments in CFL slowly. So I go 12. I let it run a couple of iterations. See that now it will be increased. Let it run a couple of iterations until it settles. And then you go 14, 16 until you reach the decided CFL. So now I go here 15. So do these changes. Okay, you can do it on the fly. Okay, I hope you know that one, but do it very slowly. Okay. By the way, also an stabilization technique for compressible cases that I have found is also sometimes you will need also to increase your viscosity. So sometimes when you start your simulation, you can go constant viscosity and you put here a large value, 10 to the minus 3. And then I slowly, probably after 500 iterations, reduce it. And then you change to your thermophysical model, the Sutherland model, okay? So that is another way to stabilize. But see that it's running very smoothly. Large time state compressible flow with shock wave. And let me go here now, 18. Okay, so if I go here, phone. Build and. So this is a validation case. I tested and retested. Actually, for me, one of the benchmarking cases, because always when I get a new release of OpenFOAM, I test it here, and I like to see the changes in numerical schemes and everything. So For me, this is part of my validation matrix, this case. So see that you start to see here the shock wave forming. Oh, yeah. So let me go. Okay, still don't have a solution there. Okay, I have one here. So let me show you. I rerun this case. So let me show you raw pimple phone. I have it here. You have it there. Also the wall resolving. So it's exactly the same. So you see it's the same numerical skin, but I started with a CFL. I control my CFL using the pimple. That control, you can only do it with the pimple only. Start with 2, then go to 5, then to 10, 15, up to 20. But you do it slowly and you will get a stable solution, no problems. So let me go Mac number. Okay. So also just to mention that I managed to do also that benchmarking, the high leaf, and also that drag prediction workshop. I managed to do also with OpenFOAM. It is very time consuming. You need to run a lot of iteration, but you can do it. But it's true that I think it can be improved a lot, the compressible solver. But as you play well with your numerics, you can get solutions. So see that at the beginning, you start to see some artifacts, okay? But that is just the initial solution. Then it will be a small transient, okay? You should be careful also the turbulent variables. So remember that those turbulent variables, in this case, K and omega, are positive bounded variables. They need to be always positive. And sometimes you may have here negative values. So you should monitor also that. So if you have large negative values, it will be better to go or to use a win. In this case, I'm using a win if I will recall for the turbulence variable quantities, but you can go linear win and you will see a little bit unboundedness, but in this case, it's not a problem, okay? It's a small value, but see here immediately, but this is a small value, but those are things that you should be also monitoring. And that's why I always monitor here, see that you have pressure forces. So on one point, you see pressure velocity here of 10,000. You know there is something wrong there going on. Okay, so see the solution. So in this case, in 4 cores, it will take about, if I will recall, like 1 hour to run. So I think I am just in time. Okay, so see that this one is 18 and you can go. So feel free to play with this case. I tested, and it can run up to 40, okay, or 50, CFL 50 with no problem. But again, you are missing a lot of accuracy. So that is not the idea, okay? And a lot of people want to get solutions right away. You will lose accuracy. Okay, so I think with this, I'm sorry that I didn't cover everything, but I hope you have an idea. Okay.
Thank you, Joel. That was really great. A lot of information. We do have one question here from Andrew. So I just want to ask this for everyone. He asked, do oscillatory gradient issues build up over time in transient solutions?
Yes. That you should be careful of that. Yeah, that can happen. And actually, the airflow case, the one I just run, if you don't use the slow limiter, the gradient limiter, that oscillation will accumulate. And actually, you will see in this solution, I don't have it, but you will see an extension artifact in the upper surface of the airfoil. So just play with that case and you use switch off the gradient limiters, and you will see that effect, and you will see those oscillations in the upper surface. And then immediately when you enable the gradient limiters, it will go away.
Okay, great. Thank you, Joel. I didn't see any other technical questions in the chat. So, and we're at 10 o'clock. So I think we're good to end. I want to thank everybody for attending. We had almost 100 participants in here, which is fantastic. I hope everyone found this educational. And of course, we did record this session. So at some point after the workshop, we'll get this posted into the proceedings for the workshop electronically. Okay, thank you again, Joel. And we'll see everybody.
Okay, thank you.
See everybody in 15 minutes in the technical sessions.
Okay.
Okay, bye now.